Hi, everyone. Welcome. Good morning, good afternoon, good evening, wherever you are, whatever your time zone is. So my name is André Carvalho, and I'm the lead for Quantum Professional Services at Q Control. And today with me, we have Michael.
Hello, everyone.
So,
I'm Michael Hush. I'm the head of quantum science and engineering here at Q Control.
All right. So we'll be, do you have the slides on, Michael?
Yes, it should be visible now. Yep.
Okay, so today we'll be talking in our webinar on suppressing errors on real quantum computers. And we have just a couple of housekeeping announcements. So the first one is for you to post your questions using the Zoom Q&A function. That will make it easier for us to keep track of those questions as we'll be answering them throughout the webinar. Also, during the webinar, we'll have some polls for you to, with some questions to answer. And at the end, we'll have a survey for you to fill in. And by completing the survey and putting your email, you have the chance to win a $50 Amazon voucher. So to give you some context on what we'll be talking today, I don't know, I mean, we have lots of new people and some people attended our previous webinar on robust control. And we presented some of our results on experiments on the IBM hardware. So the idea of the webinar today is really to answer this question: how can I make pulses that work on real hardware? So we'll have a couple of approaches to describe. So in the first one, we'll have the model-based optimization. That's going to be split into two presentations. One about pulse design, having information about your hardware. And then the second one is all about calibration and implementation on a quantum computer. And then we have the second part, which is going to be quantum control with reinforcement learning. All right, so without further ado, let's start kicking off with our presentations. In this presentation, we will learn how to create pulses that work on real hardware. It will be presented to a set of optimization tools that allows you to include information about device limitations to design pulses that are fully compatible with hardware constraints. And since we are talking about pulses working on real hardware, let's start with some of our recent results of robust pulse running on the IBM Cloud quantum computer. Here's a side-by-side comparison of the IBM native pulse and a Q-control pulse robust to amplitude noise over the course of 4 days. The pulses are implemented in parallel in all 5 qubits in the chip. The robust pulse provides a 10-fold improvement in hardware stability over time and across device, as well as a 10 times improvement in single qubit gate performance. We will discuss in this presentation all the steps necessary to achieve these results, from pulse design to calibration and implementation. Let's start with this diagram representing a simplified model of the different stages of what you would encounter while trying to optimize a gate. On the left, you have a gate that you want to apply on the system, and to perform an optimization, you need access to the pulse that will physically implement that gate. At the hardware level, this pulse will be generated by an arbitrary waveform generator, go through control lines, and finally reach the qubit. For now, let's be at peace with our ignorance about the hardware and consider the very basic model that we may have to consider for the quantum system. We have a control Hamiltonian representing the physical interaction that performs the gate, with gamma being this complex shape of the pulse. Alternatively, it can be written in terms of I and Q variables, which is more common for superconducting qubits. Here, we are writing this Hamiltonian in terms of Pauli matrices, as we are modeling the system as qubits, but we need just to take note that sometimes a better model for the system is including more levels, and that can be included in the Hamiltonian for your optimization. Finally, we can add extra terms defining the noises that may be acting on the system. Here we consider the phasing, described by this term with the sigma z operators, and also some noise on the control amplitudes. Now that we have the model for the control Hamiltonian, as well as the noise that we want to suppress, we can give this information to the Border-Opel optimizer to find the desired gate. The diagram on the left shows the steps of this process. We input the parameters of the system, like the maximum RABI rate and the hardware time resolution. We also input optimization parameters, like your target gauge, its duration, and also the number of segments that you want in your pulse. Then you create the Hamiltonian with the optimizable variables, in this case, I and Q. If you want to generate a robust pulse against a specific kind of noise, you add this term as well, and you're ready to run the optimization. Here, in this presentation, I'll be focusing on this high-level description of the optimization, but you can find the full code and all the examples we will cover in this presentation in the application notes in our documentation. So in the center figure, you see the result of an optimization of the phasing robust pulse. On the right, you see the result of the implementation of this pulse on an IBM quantum device. The experimental points clearly deviate from the expected numerical curve, indicating that something is not quite right, from our original pulse to the final effect. So a clear feature of this particular optimized gate is this fast variation and abrupt changes in the pulse values. Given that the hardware electronics have bandwidth limitations, one may conclude that this pulse may not be properly implemented in the device. So one option to solve this problem is to use Border-Opel flexible optimizer, because it allows you to include extra constraints to deal with hardware limitations. In this case, for example, we want to avoid the abrupt changes of the previous pulse. One way to do this is to impose a bound on the amount of change that can happen in the pulse value from one segment to the next. This adds a simple step in the optimization flow shown on the left. So that's this part here. The resulting pulse is smoother than before, and its implementation shown on the right is visibly better as well. Now, we could take a different approach to smooth our pulse and avoid these high frequency components of this highly varying pulse. So we can do this by including a filter. This is described in the Hamiltonian on the left. We are applying some linear filter on our variables I and Q. So again, this can be easily incorporated in the optimization flow on the left. The pulse obtained is smooth and suppresses frequencies above a given cutoff that's user-defined. You see again a good agreement between the experimental data and the numerical simulation. This diagram here summarizes what we discussed in the previous slide. So we use information about hardware constraints, in this case, the bandwidth, for example, of your waveform generator. One can design a pulse that's compatible with your device. Now, there is yet another use for this filter feature of our optimizer. So after the program pulse is created by the waveform generator, it then travels through control lines until it reaches the qubit. In this process, the pulse can be distorted according to the channel's transfer function. This means that the pulse reaching the qubit is different from the one that you designed. This would lead to bad results. However, if you know the transfer function of your control lines, you can add this information to the optimizer, which will then find the pre-distorted pulse that will lead to the desired pulse shape reaching the qubit. Now that you know what the flexible optimizer is capable of, I would encourage you to go and explore our application note on constrained optimization. It contains multiple examples of what I covered today and much more. There's a version that you can access in our documentation, but also a Jupyter notebook that you can execute if you sign up for our free trial. So in summary, Border-Opel has a series of features that allow you to refine your optimization based on information of your device. But now, what happens if you don't have this kind of information? How can you take advantage of pulse shaping on someone else's quantum computer? We'll discuss this in the next presentation.
Thanks for that presentation, Andre. Oh, who's coming back now? I'm just going to set up our first poll. We're already getting some questions through, which is great. Let me put this on. Here we go. It's just a couple of questions so we can get to know everyone a bit better. So we've got some chat as well. I just remind everyone, if you have any questions, use that Q&A button down the bottom and we'll answer whatever you would like. And you're welcome to add questions as we're watching the presentations as well. So Andre, the first question we have is, does the implementation of Q-control error suppression increase the quantum volume of IBM systems?
Right, so we don't really have exact calculations of quantum volume, but what we have is really experiments where we concatenate multiple gates so that we look more at the depth of the circuit. But yeah, so that's something that's on our roadmap to explore on the IBM systems.
Yeah, I would highlight that we expect that it will. So the errors that we're dealing with should improve quantum volume, but we're completing the set of gates. So we're also looking at controlled gates at the moment and learning more about the cross-resonance gate in IBM, which is, whenever we try and optimize something, as you'll see in the next presentation, there's a lot to learn about these models. We also have a great question from Kaylin. So what about noise that is not described by Hamiltonian dynamics, in particular depolarizing channels with cross operators?
Right. Okay. So as there is already an answer there written down, but so we have the capability of actually doing some open systems, and that's on the way to be implemented in our product. So that's in our roadmap as well. And in that Hamiltonian that we have, if you've seen, so I put there the sigma z operators, and then we had a term at the front that's a stochastic term that's a slow varying noise process. So that's how we model those operators there.
One other very good question. So how does your optimization and pulse control connect with quantum error corrections?
Right. So I guess a good way to put that is that our controls, they lower the threshold for error correction, right? So what we are doing is just reducing the amount of errors that you have in your gates. And then if you perform, for example, given gate an operation, then you can correct later on using error correction. But what our gates do, they really lower the threshold by reducing the error.
Yeah, so that's a really important thing to highlight, is that they're completely compatible. And in fact, yeah, complement one another. So you're best off using both. I'm just going to end the poll to get some information. So it looks like about half of, well, yeah, around half of you have used IBM in the standard way. And it's good to see quite a few people using custom pulses through open pulse as well. Yeah, just wanted to highlight that the best way to get access to, the best way to use the control solutions we're presenting on IBM is through open pulse control. Currently, that's just available on one device for public use. But if you are interested in that and would like to know a bit more about this process as well, feel free to contact us. Another question is, yeah, so at least 34% of you, a greater amount of you have at least this pulse level control, which is required on perhaps a different platform. And if quite a few people have not tried pulse Opta's optimization yet, but almost half of you have, which is really good to see. Almost half of you at least intend to. Yeah, I'd highly recommend you have a look at this feature after the webinar. So with this, I think we've addressed many of the questions. There's just one more that's come up. Will there be any impact of your proposed technique on quantum networking?
Oh, that's one that I haven't thought about, but I would imagine that anything that reduce errors is something that will improve any kind of quantum technology, right? So, and that's
in particular, if there's light atom interactions, I expect that there's
right.
a great potential for these techniques as well in those settings. Yeah, excellent. They're very useful and repeater, so to speak. Okay, well, let's start the next presentation. And again, if you have any questions, just put them in the Q&A as we go along. In this presentation,
In the previous presentation, you learned how to create robust pulses that are compatible with your device by adding real hardware constraints to the boulder optimizer. In this presentation, we'll discuss what to do when such information is not available, as is in the case when you're running your gates on someone else's computer. To achieve good results in this scenario, the secret is careful pulse calibration. Let's start our description of calibration using the example of pulses being implemented on a real device. We'll be using IBM Q as it allows users to design their own gates on some of their chips using Qikit Pulse. The Q control pulses that we discussed in the previous presentation were given in terms of the physical quantities I and Q. The IBM software uses a different input. Those are dimensionless quantities. Task is to map the real amplitudes I and Q into the hardware inputs AI and AQ. For that, we first select a given value of AI and send a constant pulse with this amplitude into the system. The qubit will be excited, and by varying the amount of time the qubit is exposed to this drive, you observe the system performing RABI oscillations, as you see on the left. You can then fit the experimental points and extract the value of the RABI rate corresponding to your original choice of hardware input, as it's shown here in this plot on the right. So you picked a value on the horizontal axis, did the fitting, and found which value on the vertical axis they correspond to. You now repeat the same procedure for another value of AI, another point in the horizontal axis, and by performing another fit, you find the other value. And by doing this for all the range that you want to calibrate, you establish this mapping between the RABI rates and your dimensionless hardware input. So one advantage of this calibration is that it is general in the sense that it's valid for any pulse, as we assign a value for each pulse height. You can then verify your calibration by taking one of your pulses and implementing on the device. In this case, I used the dephasing robust pulse, here shown on the left, that we discussed previously, and its time evolution is shown on the right in terms of the three components of the Bloch vector. You can see that there is a good agreement between experimental data and the theoretical prediction. So even though this is a good indication of your initial calibration, to really test its accuracy, you should do a different experiment. The experiment I'm referring to is repeating the gate multiple times. If there is an error in your initial calibration, this pulse repetition will amplify its effect and help you recalibrate the gate. So in this plot, we show the experiment done for the IBM D4 X gate and our dephasing robust pulse. You can see the quick drop in fidelity for the robust pulse, but you can also see that it recovers later on. This is an indication of coherent errors as illustrated in this diagram on the right. The red curve shows RABI oscillations, but if your pulse under-rotates slightly, this error will add up and look like the oscillatory curve, similar to the experimental results. So the question is, how can we fix this? To get a better idea of what the pulse is doing in the system, we added a scaling factor to our pulse and scanned it for multiple pulse repetitions. So this is described by this equation at the bottom here. You can see that the results for the experimental runs shown on the right are close to our numerical simulations on the left, being a little bit more different in this central region here. The white dashed line corresponds to no scaling. That is, we are back at that original RABI rate calibration. For the numerical solution, this coincides with this band of high fidelity for a wide range of pulse repetition. For the experimental results, this looks shifted. And to take advantage of this band of high fidelity, we have to rescale the pulse up to this scaling factor shown by the dashed pink line. If we now run the pulse again, but now rescaled by that scaling factor that we just found, we see that not only we get rid of that typical miscalibration curve, but that also our pulse outperforms the full IBM gate. So this successful calibration is really encouraging, but does it always work? Well, it doesn't. This plot illustrates the same 2D scan as before, but now for a pulse that we designed to be robust for both the phasing and amplitude noise. The numerical solution shows a broader band of high fidelity, as you would expect for a pulse that was created to be less sensitive to fluctuations in its amplitude. The experimental result, however, shows a completely different picture. The pulse reaching the qubit is very different from what we planned. Let's look at what may be going on. We have the pulse that we created, we send it to the hardware, and the evidence is that it does something else, as if it were a completely different pulse. As we have discussed in the previous presentation, hardware constraints can deform pulses before they even reach the qubit. Before, we explored how our knowledge about the hardware can be used to design better pulses. Here, we don't have this choice. Well, since the effect we're trying to do is undo pulse distortion, the strategy here is to use a two-parameter differential calibration. We call it differential calibration because it allows the I and Q components to be scaled relative to one another, deforming the pulse. So after obtaining this relative scaling, we perform a second step, so it's a second overall rescaling to maximize the gate fidelity. The hope here is that this differential calibration fixes the deformation induced by the hardware. So before I move on to show results of those pulses in the real hardware, I'd like to again point out to our documentation, and specifically for the application notes that we have on calibration. It has all the codes and all the steps necessary to run a pulse calibration on the IBM Q device. And if you go to app.qcontrol.com, you'll find an interactive version that you can execute if you sign up for a free trial. So let's then go to the results that we get from those calibrated pulses. So the results in this plot show the successful calibrations of 3 different robust pulses. One that is robust against the phasing, another one that's robust against amplitude, and a dual robust that's simultaneously robust to those 2 kinds of noise. They again beat the out-of-the-box IBM default pulse. The curves in the plot indicate a fit using this function here at the bottom, so which allows us to extract both the errors coming from rotation, written as this epsilon here, as well as exponential decays. So once with these errors at hand, we can estimate an overall error per gate, as illustrated in this plot here. So the points are the error per gate on a given day for the phase and amplitude robust pulses, as well as for the IBM default, for all 5 qubits in the Valencia backend. So the pulses were applied simultaneously in all the qubits, and we see not only perform improvement from our pulses, but also a homogenization of errors across the device, meaning that all qubits perform similarly under the robust pulses. Finally, we come back to where we started, a plot that summarizes the improvements from our robust pulses. The difference between the bright colors on the IBM pulse as compared to the homogeneous dark colors, meaning low errors, for the Q-control solutions is very evident. It shows in a single plot the overall error reduction with robust pulses, the spatial homogenization of errors across the device, as well as calibration stability. Note that the Q-control pulses were calibrated only once. They were calibrated on August the 3rd, while the IBM pulses are calibrated daily. So this completes the model-based optimization part of our webinar. You have been introduced to the tools necessary to create robust pulses that work on real devices. If you have information about device imperfections, you are now in condition to include the relevant constraints in your own optimization to design better pulses. If you run your gates in someone else's phone computer, you can use the calibration strategies discussed today to successfully implement your pulses in these devices. But there is more. I'll leave you now with the final part of our webinar, where Michael will be presenting a different approach to optimization using reinforcement learning.
Thanks again, Andre. Let me just turn on the next poll. Great. So we've had quite a few questions come through. I think there was one, actually I just want to quickly address. Someone earlier asked, what's the difference between GRAPE and what we do? So I just wanted to highlight that everything that we've designed, Grape is primarily designed so it's each segment has to be optimized. It's structurally designed to be piecewise segment. I really wanted to highlight that our optimization engine goes beyond that. So it can be constituted of whatever arbitrary functions you want. So it can be, you can use crab style optimizations, you can do grape style optimizations, but our optimizer is much more flexible and allows to take into account any experimental constraints that you may have, as Andre showed. So we also have a few fresh questions that just come up. Nate asks for the amplitude robust pulses, how much do you suppress amplitude noise?
Right. I don't really have a number for that. What we have is it depends on the pulse. This one we were just looking at the scaled repetition. So basically what we can say about that is just, for example, that we calibrated that pulse in 1 day and that calibration just remained good for 5 days. So this tells you how much insensitive it is to fluctuations that happen throughout that whole period. We had some experiments that we ran on RMonk where we actually did a scan where we artificially added noise to our control and just scan that to see how much it could support. But that one was a very long pulse, so it could support up to 20% basically noise in your amplitude. But for this one specifically, we didn't do this specifically scan.
We've got another good question about regarding over and under rotation errors. How do these solutions implemented by Q control compared to naive controls approaches such as phase alternation, so other robust solutions from the NMR literature?
Right, so the under and over rotation errors here. So what we did there on the IBM was mostly a calibration issue, right? So in terms of designing the pulses, we could think that the under and over rotations are designed with this amplitude thing in mind. So the way that we do is, as we described in the previous webinar, we can put the link somewhere in the chat, but we have the filter functions and we use the filter function component at 0 frequency to make sure that the optimal control really has a low sensitivity to response to that kind of noise.
Yeah, I just wanted to highlight there as well,
Michael.
Yeah, and an extension of that. So the underlying physics of robustness, there's definitely a connection between the history of NMR robust control. But I really wanted to highlight when you use our optimization engine, the pulses are typically much shorter. So in NMR, the standard particular applications, I think it's a BB1 is the amplitude robust version. So that is, our pulses tend to be shorter, but achieve the same degree of robustness to error. And you really get a massive advantage when you concatenate multiple things. So if you want robustness to amplitude and to phasing, they can be much quicker, up to 4 or 5 times quicker actually than certain concatenate pulses sequences. Oh, and lastly, I just wanted to highlight, you can also combine leakage. So in addition to all these robust features, you can also add additional transitions. You can go well beyond just a qubit. You can deal with multi-dimensional systems. Yeah, and compared to the NMR literature previously, there's some deep connections with the physics, but our tools can stretch and are much more widely applicable to more systems with many more constraints. Okay.
We had one here. Oh, what's that? So we had one here asking about how would you explain that the dual robust gate performs worse than the dephasing gate? So that's an interesting one. And because when we design those pulses, of course, I mean, one issue is really the experimental one in a way that those pulses, they have different shapes, they have different frequency components. And there's, of course, the issue of how they go through your hardware and how they implement. They may have, for example, frequency components that couple to other qubits in the system or the 2-level systems in the system. We don't know that. But from the point of view of designing the pulses, what happens is that when you enforce this dual robustness, you are trying to enforce robustness against dephasing and also against amplitude. So what happens is that in the end, it's slightly less robust to dephasing than one that was only designed to be dephasing robust. So that could be one thing that's going on there, apart from the fact that those pulses have slightly different durations, and that could make a difference as well.
I think we might answer the last few questions a bit quicker because we'll try and move on to the next section. But everyone, I just ran the poll. It was interesting to see that most people went for reduced error per gate as the most important thing. Fortunately, we can actually provide all of these parts, as Andre showed. Yeah, that's interesting. I guess the thing I would highlight, there's perhaps a representation of error homogenization across multi-qubit devices, but I would say there's a lot of opportunities for changing the way that you route your algorithms if you get homogenization of your errors, which could have quite significant effects on the algorithm. Someone also asked a great question. What document would you recommend for someone new in the field? So I'd highly recommend actually you go to our website, sign up with app.qcontrol.com. And we have these things called application notes, and we have a variety of application notes which kind of show step by step what robust control is. We've also done a webinar introducing the concepts of robust control, so you're welcome to watch those videos, which are all on YouTube. And there's also a variety of, if you don't want to sign up just now, you can go to docs.qcontrol as well, and there are a variety of documents there which you can read, which explain all of the physics underlying what we're showing you today. One last question before we finish. So in this context, does amplitude error mean calibration error? Maybe Andre, you can explain the difference.
It's more general than that, right? So the amplitude error could be anything that's noise in your controls, right? So the calibration error is just an instance of that, right? So the calibration is just a fixed kind of error, coherent error in the way that you set up your pulse, while you could have just kind of random variations on the amplitude of your noise, and that's what we are calling amplitude noise here.
Great. Well, I'll set up the final part of the presentation.
Give a preview of our recent work using reinforcement learning to improve the fidelity of gates on IBM superconducting devices. So why reinforcement learning? Reinforcement learning has been used to create AIs capable of beating human players at video games and is now state-of-the-art for certain control tasks in robotics. Here we have a demonstration of a reinforcement learning AI playing StarCraft 2. The AI was able to reach Grandmaster level, ranking it above 99.8% of all human players. That's quite a bit higher than my ranking when I used to play. Next, we can see a reinforcement learning controller that was trained to complete a Rubik's Cube with a robotics hand. This is a remarkable feat of control and was done through a series of training the AI with simulations and real robotic hand movements. I'll skip to the end so you can see that it actually did solve the puzzle. And there we go. At Q-Control, we have been exploring if the power of reinforcement learning can be brought to the domain of quantum control. In Andre's presentation, we saw how model-based optimization can be used to create robust, high-fidelity quantum gates. Reinforcement learning is a different approach, where no model is required. The learner creates an optimized pulse by doing experiments with the quantum device itself. This means characterization of the device can be skipped entirely, making reinforcement learning typically quicker at finding an optimized pulse than the model-based approach on an uncharacterized device. Furthermore, reinforcement learning can discover and exploit new physical mechanisms that you are not aware of. The disadvantage of reinforcement learning is that the learner can't tell you how it found a solution, so you won't get an understanding of the physics or the noise processes of your device. In contrast, creating a good model of the faults and physics is a requirement for model-based optimization. I should note that once you have a model, model-based optimization is very quick. Optimizing a pulse numerically is very efficient with Q-Control's Boulder Opal package, and then calibrating the pulse on the device typically only requires a few measurements. Reinforcement learning training, on the other hand, can require thousands of experiments. So which approach is better? Q-Control's answer is ¿por qué no los dos? Why not both? Here at Q-Control, we believe in delivering powerful and easy-to-use tools for all applications. Hence, we are creating state-of-the-art reinforcement learning features for our products, along with our already released model-based optimization tools. We are also investigating combining the approaches, where we accelerate the training process of reinforcement learning using partial model information. Our first demonstration of performing quantum control with reinforcement learning is on the optimization of single qubit gates on IBM Q. We have demonstrated a learner can discover a faster pulse for implementing a high-fidelity X90 gate than IBM's default pulse. Before I present the result, I'll explain how we put a learner in control of a quantum computer. I'll create a bridge between the terminology used in quantum physics and reinforcement learning. The quantum computer is referred to as an environment for the learning agent. The agent is tasked with achieving a goal, performing a high-fidelity X90 gate. An agent is able to make a variety of actions on the environment, in our case, applying pulses to the quantum computer. The agent learns to reach its goal by being provided with the state of the environment, a set of measured observables, and a reward based on how close it is to its goal. Our reward is derived from the gate fidelity. The agent performs many experiments trying different actions and getting information about the device through states and rewards. The learning algorithm uses this information to improve the performance of the agent. After a number of experiments, the learning algorithm will create an agent that achieves the goal of creating a high-fidelity X90 gate. Let's break down this process step by step. The first part to understand is the environment and state. The agent deploys a series of pulses to the quantum computer. Full tomography of the quantum state would require too many measurements, as a real qubit is not just a two-level system, but instead a multi-level oscillator. So instead, an incomplete measurement of the quantum state is used. In this result, we calculate an estimate of the three Pauli operators. The estimates were calculated by averaging 256 runs of the quantum computer. Even though the estimates are noisy, our learner is still able to use this information effectively. The agent then takes this state and uses this information to decide what action to take next. In our experiments, we treat each piecewise constant segment of the pulse as a step. In each step, the agent takes the state and uses a neural network to decide what action to take on the next segment of the pulse. We quantize the amplitude of the pulse so that the learner chooses from a finite set of options. A full gate pulse is called an episode and is made up of multiple steps. Note that the agent will perform multiple experiments to complete just one episode, as it needs to measure the state of the quantum computer after setting each value of the segment in the pulse. This allows the agent to create an understanding of the dynamics of the quantum device. Once enough experiments have been done to create a complete episode, we can calculate a reward. We could in principle calculate a reward for the agent at the end of the episode using the state. However, we found this reward was too noisy to get high fidelity gates. So instead we calculate a reward using a weighted sum of multiple repetitions of the full gate pulse. This allows us to boost the error signal above the measurement noise. This is a similar trick to what Andre presented earlier to calibrate pulses. The weighted sum provides a precise estimate of the fidelity of the gate, which we use to reward the learner. The final element of the process is the learning algorithm. The learning algorithm takes into account the actions, states, and rewards and improves the intelligence of the agent. We have performed experiments with a wide variety of learners, including deep policy gradient, deep Q network, advanced actor critic, proximal policy optimization, deep deterministic policy gradient, twin delay DTBG, and soft actor critic. We will include a detailed comparison of these algorithms in future work. All these learners have hyperparameters that must be tuned before they can be used on a real experiment. We have simulated a quantum computer using Boulder Opal, which can take into account realistic non-Markovian noises to tune these hyperparameters. I've now established how we connected our reinforcement learning algorithm to IBM's quantum computer. We have been training our reinforcement learner on IBM's real devices and have some initial promising results, which I'm happy to share with you today. First, let's have a look at the convergence of the training process. Here we have a plot of the mean fidelity and infidelity of the full gate pulse as a function of the number of episodes we trained with the learner. We run the learner in batches of 25 at a time, and the fidelity is averaged over this batch. The fidelity is plotted in pink on a linear scale, while the infidelity is plotted in purple on a logarithmic scale. We can see the learner converges to a plateau just above 10 to the minus 4 after around 4,000 episodes. It's important to note that this training data was taken over days. The learning algorithm remains remarkably robust, converging to a good solution even with the recalibrations that are performed at the end of each day. At the end of this run, the best pulse was selected from the 25 in the last batch. At the end of the training process, a complete randomized benchmarking characterization was performed for Q-Control's pulse and IBM's default pulse. On this particular day, we can see that Q-Control's pulse has a gate error on the order of 10 to the minus 4, which was slightly smaller than IBM's error. This error measurement fluctuates, and on other days, IBM's pulse would be slightly better. In any case, we believe that the learner was able to find a pulse that is T1 limited with equivalent to performance to IBM's default pulse. The key advantage of Q-Control's pulse is that it is 20% faster than IBM's, allowing more gates in a shorter amount of time. Looking at the shape of the pulse, we can see the learner is using both the I and Q modulations, and that the pulse envelope is not simply square or Gaussian. It's difficult to determine what physics the learner may or may not be exploiting, especially because the pulse experienced by this qubit is subject to hardware distortions that we are not aware of. But we have identified that the pulse is at least non-trivial. The remarkable robustness of the training process suggested to us that the pulse may be robust as well. To investigate this, we measured the average gate fidelity of Q-Control's pulse and compared it to the default pulse from IBM over 8 days. We can see that Q-Control's pulse has comparable performance to IBM's default pulse over a week. What's remarkable about this result is that Q-Control's pulse was not recalibrated at all over this period. The absolute values of the pulse remained fixed, and it stayed T1 limited over the entire testing period. In contrast, IBM's default pulse was recalibrated daily and has notable changes to its absolute values day to day. This concludes our preview of Q-Control's work on quantum control with reinforcement learning. We are continuing to improve the result and investigating creating even shorter pulses. We will present further details on our reinforcement learning work in a future webinar. So make sure you're subscribed to our webinar series to hear more about Q-Control's latest developments.
Thanks, Michael. This is really great results there. Okay, so let's go to the Q&A. So this one here, I think you probably answer a little bit after the question came. So it said, this is definitely a great application and merging of machine learning with quantum computing. The question is, how long does it take for this learning for a full gate set? And does this have to be recalibrated regularly as the environment might change? Also, does the learning start with the theoretical pulses and then improve, or it starts with no information?
That's a great set of questions. That covers a lot. So first thing I'll say is these results, it's no information whatsoever. So the learner learns everything from the device. We consider that important, I think, just as sort of an interesting feature of this learning demonstration. In future, we might not do that. In future, there are certainly opportunities to give the learner initial information with partial model information in an attempt to accelerate its convergence. But for these demonstrations, it's just completely learning itself. Of course, because of that, it does take many experiments. So I did mention that it took days to run, but this is largely because of the IBM. When you run a result on IBM, you're competing with other people using that device. So there's a queue and you have to wait quite a long time. In the end, the number of experiments required is on the order of thousands to perhaps, well, in terms of individual circuits, it's on the almost tens of thousands. But depending on your configuration, if you're working with superconducting qubits, that can be run relatively quickly. In terms of the full gate set, yes, you would need to do this for each particular gate. And we're currently also applying this to 2 qubit gates, but we suspect that they'll have similar improvements. I guess there's a continuing open question, which we're also very interested at Q-Control. What's the best balance between reinforcement learning and model-based learning? But I think we're pretty confident that we could hybridize the approaches. So this initial demonstration is really focused on just showing that a learner is capable of completely learning something from scratch. But we are certainly interested in quite significantly accelerating the amount of, reducing the amount of training required. And to highlight the potential there, just one last, it's such a good question. Sorry, I'm going for a bit long about it, but that robot hand I showed you at the beginning of the video, so that was actually trained with simulation as well. So there really is, and there's some special techniques you can use to kind of add noise to the way that your simulation adds to ensure that it has a better chance of then being capable of running on a real device. So there's a lot of opportunity there to hybridize approaches.
All right, so we have quite a few questions coming up. So one here, which learning algorithm is the fastest in accordance to your experimentation?
Sorry, which was the, sorry, I started reading them myself, so I missed it.
So it's asking which learning algorithm is the fastest.
Which learning? I can't, we will be telling more about the particular algorithms we tested in a further publication. For now, we're still working on that, and we'll let you know. We'll let you know when we've completed all of the verification, but those results will be presented soon.
Right. Which answers the other question here, which was exactly asking for a reference or if we were going to have that in a publication. So just answer that. Another question here, is there any other way to define the reward other than the weighted sum for quantum computing?
Yeah, so there is a careful between the number of experiments you have to do and because you want to, of course, minimize the number of experiments so that your training, it works well, while still giving it enough, information to achieve the goal. In principle, you can give it any reward. But we found that just simply trying to calculate a single fidelity from a basic tomography of the state, it's far too noisy. So you have to employ some trick. The one we did, I think, works pretty well. And is related, we learned this basically from all of our work that Andre did earlier with calibration. That kind of inspired us to use the measure we did.
Right. Let's see, another one here. Early in the presentation, it was said that so as X, as Y, and as Z are calculated for each pulse, and that each pulse is run 256 times. Since they do not commute, is each pulse run 256 times total or 256 times 3?
Yeah, so that's right, they don't commute. So we ran them every single one individually. And so, yeah, you had to run them 256 times 3. And just to highlight that, yeah, we obviously have to restart the pulse. When I said state, like what we're doing is every single time we restart the quantum computer in the same initial state, run it 256 times up to the position we are in the pulse, and then measure each observable separately. I'll just quickly highlight, so the polls came in, I sent a poll to everyone what their experiences was with machine learning. And looks like quite a few people have been doing supervised learning, which is good to see. And also that quite a few of you actually work in quantum machine learning. I did want to highlight that, of course, what I'm presenting today is not quantum machine learning in the sense of using the quantum device to do machine learning, but instead what we're trying to do is use traditional, well, advanced machine learning techniques, which already have been shown to be good at other techniques, and applying them in the quantum domain and seeing the potential there.
Right, so we have quite a few more questions here. Do you apply RL to the simulation as well, or just with the experiments?
So the thing I wanted to make clear there. Okay, so there is no simulation done before these experiments. They literally start afresh on the experiment. We have also been doing separately to this a variety of simulations and then running reinforcement learning on that. Yes, and we've been completing those simulations using our Boulder Opal tool. So our Boulder Opal tool has a kind of a more detailed non-Markovian model for the noise on the systems, which we found was quite important to be able to simulate these quantum devices effectively. And so if we can simulate them effectively, we're able to use those simulations to tune a lot of the hyperparameters and other things that are required to get a learner working out of the box. Because if you try to use them naively, often they don't necessarily converge.
Right, so very interesting reinforcement learning results. Have you tried any other optimization methods which could possibly minimize the number of experiments needed to find a solution, such as Bayesian optimization?
Yeah, so we, well, yeah, on that. So I personally have done work with Bayesian optimization on online optimization for quantum problems as well. It's something we're also looking at. I think there's a real novel application of reinforcement learning. Reinforcement learning is very interesting I'd say what's cool, like saying cool isn't very technical, but what's exciting about the reinforcement learning is it really does take information about the state and it learns a dynamic map. And because of that, like, I think that gives it a real power to solve very hard problems. And it's probably the reason why it is so effective in these things like video games and other kind of more advanced robotic tasks. And you're seeing in other domains where you're trying to solve really challenging problems, that the Bayesian techniques are not so much an application as these reinforcement learning techniques. Of course, in practice, if you want to get something tuned really quickly, there is real potential for Bayesian techniques instead. And we're, of course, going to make them available. As I said in the video, we're actually looking to provide all tools to make things as easy as possible for you. We're not necessarily going to commit to anything in particular.
All right, so there's a question here, but if you have to solve for the state at each time, then there's not a restriction?
So the cost at having to, actually having to evaluate the cost at, the cost of having to find the state of each thing is you have to do more experiments. And so that's the trade-off. But the idea is that potentially doing those extra experiments make really reinforcement learning algorithm more intuition about what's going on in the device and be able to provide even better solutions that other techniques might not have been able to achieve. And then we've got one more question left. Where do the logic of the model-based and reinforcement learnings reside, in hardware or software? So I should say, with regard to everything that Andre did, his results are all available today in Boulder Opal, and all of that model-based optimization routines and characterization, that all goes, you install a local Python package, which you can integrate into your quantum computer, into your optimization routines. And that small Python package sends off calls to our web API, where we spin up a variety of servers to solve the optimization problems very efficiently. And so that's the hybrid. So it's going to reside somewhere in the cloud and like a Python installation on your device. The machine learning, again, it's actually still in research phase. We're heading towards a product rapidly, but we'd expect something similar where you're going to use a combination of our cloud infrastructure for the really difficult computations and then running it locally on your machine. But we really want to highlight that we're focused, of course, on performance. And so everything that we do at Q-Control, we make sure that our solution is going to be rapid and efficient.
So I have a couple more questions here. You said that the RL method can take non-Markovian noise into account. Can you do that with the model-based optimization also?
Yeah, what I meant to say there more specifically is that we trained our reinforcement learner on a simulation which incorporated non-Markovian noise. So that's what I meant to say. And when I say non-Markovian noise, I mean the noises that Andre actually mentioned in the model-based optimization. So correlated over time and space. Yeah, so they are, of course, available. The non-Markovian models are also available in all of our model-based optimizations because they use the same engine. Our simulation and optimization engines are connected. Cool, I think that, So one more question on how do you model the noise? So in the reinforcement learning case, we simply let the learner learn the noise itself. It develops its own model. The machine itself provides all the noise we need. When we're doing our simulations, we add a variety of noise processes, whether it's dephasing processes, amplitude miscalibration, the thermal fluctuations due to the state preparation, and also the measurement span. All of these noise processes we need to take into account to give a reasonable environment for the learner to be trained on. And all of these things can also be taken into account in our product.
All right.
Cool, so yeah, if there's no more questions, thank you all for attending. So there is, when you finish, there will be a final survey you can fill in. If you fill that in, you'll go into a draw for a $50 gift voucher. So please do that. Otherwise, thank you again for your time, and please subscribe to our webinar series for more results as they come out.
Thank you.
Thank you, everyone.